So our next task is to take a look at some examples of groups that are not abelian. In other words, their operation isn't commutative. I get a different result if I do the operation on the same pair of elements in one order versus the other order. So far we've seen examples of groups where the operation was just some souped up version of addition or multiplication of integers. Both of those are commutative. So let's look at some examples that are not. We're going to start with the so-called dihedral group. And when we say dihedral, what we mean is we're going to look at the symmetries of, in this case, a regular polygon. And those symmetries are going to be the elements in our group. The operation in the dihedral group is the composition of these symmetries. In other words, I apply one symmetry to the object and then I apply another symmetry to the object. That would be the composition. The net result would be the composition of those two symmetries. So let's take a look at an example by looking at the dihedral group of the square, which we're going to call D4. So here's a regular square, right? Square is a regular fourgon. And let's think about what we can do to this square that would be a symmetry of this square. What are the different ways in which we can transform this square in a rigid fashion, so the area stays the same, right? Such that it lays on top of itself congruently at the end of that operation. So we're just going to look for what are the things we can do to this square that leave it in place. Those are going to come in two different flavors. First of all, the rotations of the square, and second of all, the reflections. Let's start in the first column by looking at the various rotations. What can we do to this square by rotating it in order to leave the square in the same place? Well, the most basic rotation we can do is a rotation by 90 degrees. If you rotate a square by 90 degrees, that square is in the same place where you started. We're going to call that rotation. Let's think of it as a counterclockwise rotation by 90 degrees. We're going to call that element R. So there's the first of our symmetries. But of course, this being a group, we can take and operate on elements. So we can take this R and compose it with itself. In other words, rotate by 90 degrees twice. What do I get? A rotation by 180 degrees. Likewise, if I do it 3 times, I get a 270 degree rotation. If I do it 4 times, I get a 360 degree rotation. But what is a 360 degree rotation? But no rotation at all. So actually, if I compose R with itself 4 times, what I get is the identity transformation. Doing nothing is still a symmetry of this group. And in fact, that's the symmetry which, when we compose it with any other symmetry, gives us the same thing back. So there's the identity element. We're going to think of it like it's a rotation. The other flavor of symmetries in the dihedral group are the reflections. So for example, this square is symmetric about its horizontal axis. Let's call that reflection the element T. There are a variety of other axes on which we could rotate the square as well. What about the vertical axis? Let's call that S. Well, it turns out that S isn't so different from the elements that we already see in this group. In fact, it turns out, and you can check this, that this reflection about the vertical axis is really the same thing as the composition of T with R squared. In other words, rotate twice, rotate by 180 degrees, and then reflect. Likewise, the other axes of symmetry, the two diagonals, can also be described as compositions of our basic rotation by 90 degrees and our basic reflection across the horizontal axis. And this list of 8 elements is the elements of D4. Now, I promised that these groups would not be commutative. So let's take a look at why the dihedral group is in fact not an abelian group. So let's look at what is the element RT, and we're going to contrast that in a second to what is TR. RT is going to be obtained by first reflecting the square and then by rotating the square. Notice that I'm going from right to left in this example. When we write down the elements of non-commutative groups, non-abelian groups, we tend to think of them as operating from right to left in the analog to how matrices act on a vector from right to left. It's just a convention. Don't worry too much about it, and we'll see how it works in this example. So what is RT? Well, T, which is the first thing we'll look at, describes flipping the square about its horizontal axis, followed by R, which means rotating that square 90 degrees, counterclockwise. So at the end of the day, if I started with 1, 2, 3, 4 labeled the way that they were labeled, what I end up with is 3, 2, 4, 1. This. So that's how we can think of the symmetry RT. What about TR? If I start with 1, 2, 3, 4 again, and I first apply R, the rotation by 90 degrees, then I end up with the labels 2, 3, 4, 1 like this. Then, applying my reflection T across the horizontal axis, I end up with 1, 4, 3, 2. So the net result of doing TR, which is rotate first, then reflect, is different than the effect of doing RT, which is reflect first, then rotate. So clearly this is not an abelian group because these two elements, R and T, don't commute one with another. In fact, we can say a little bit more, that RT is really the same thing as T times R cubed. One of the ways of defining the dihedral group is by writing down the two generators, the reflection and rotation basic generators T and R, and then writing down little equations, little relations like this one, RT is equal to TR cubed, we can actually completely define the dihedral group by writing down things like that. But for now, let's not worry about that detail. Let's just notice that this is an example of a group that's not abelian, because R and T clearly don't commute one with another. Our next and last example, as we'll see this semester at some point, is almost a universal example, that all finite groups have something to do with this example that we're going to look at right now, the symmetric group on n symbols. Now, don't be fooled by the word symmetric here. We just looked at the dihedral groups, which were symmetries in a geometric sense. Here, when we say symmetric, what we're actually going to be talking about are permutations. Permutations of a set of symbols. In other words, ways of rearranging a set of n symbols. So our first example is going to be the symmetric group on 4 symbols, where we're going to take 4 symbols, and we can call them anything we want to. I'm just going to call them A, B, C, and D. And we're going to look at all the different ways in which we can rearrange those 4 symbols. Each of the rearrangements, each of the ways in which I can write the letters A, B, C, and D underneath A, B, C, D here, any ordering, is going to give me one of the elements of the symmetric group on 4 symbols. So let's start to list some of them. If I just write them in the same order, in other words, if I do nothing to permute A, B, C, D, then what I really get is the identity element of the symmetric group. After that, if I want to actually start doing things, I might start simple, by maybe just transposing the A and the B, swapping the first entry and the second entry, the first symbol and the second symbol. So 1 goes to 2, and 2 goes to 1. In so-called cycle notation, we write that as 1, 2. So cycle notation, we're going to use that to represent the elements of the symmetric group in a more or less convenient way. Well, there are other cycles I can write down. For instance, if I swap the first and the third, or the first and the fourth, second and third, second and fourth, third and fourth, I have actually 6 different ways of just swapping 2 elements to get a permutation of the symmetric group. So there are 6 distinct what we call 2 cycles. Well, what if I extend the length of my cycle a little bit? Let's say I take the first symbol and I put it where the second was. Then I take the second and I put it where the third was. Then I take the third and I put it where the first was. Then I get a symbol, a permutation rather, which in cycle notation I'm going to write as 1, 2, 3. I'm going to call that a 3 cycle. There are a bunch more 3 cycles we can write down also. As it turns out, actually, there are 8 distinct 3 cycles in the symmetric group on 4 symbols. Each of them corresponds to a way of taking 3 of the symbols and doing musical chairs, or sort of going around the table once with them. And the 4th symbol, the one that's not engaged, actually just stays where it is. Like in our first example, D stayed where it was, but A, B, and C all did a little rotate thingy. Likewise, of course, we can do 4 cycles. Take all 4 of the elements and shift them all one place over to the right, with the D at the end going all the way and circling back to the A at the beginning. That'd be a 4 cycle, 1, 2, 3, 4. And we can write down a bunch of different 4 cycles as well. It turns out there are 7 different 4 cycles we can write down in the symmetric group. And this is almost all of the elements in the symmetric group. The ones that we're forgetting are those which we get by taking 2 different cycles and composing them together. So for instance, if I swap A and B, and I swap C and D, we can't really write that as a single cycle, but we can write it as the product of the cycle 1, 2, that transposes the first 2 elements, and 3, 4, which transposes the third and the fourth elements. So that's a product 1, 2 times 3, 4. And it turns out that there are only 3 distinct versions of those in this group, so giving us 3 what I'm going to call 2 plus 2 cycles. Okay, so it's a product of 2 cycles, each of which has a length of 2. Combine that with our one identity element, and this group has a total of 24 elements in it. Now, is this commutative? Well, of course not, right? It was one of these examples where I was going to promise that we don't have a commutative operation, so let's see why. Let's take 1, 2, and 2, 3. So the 2 cycle that transposes the first 2 elements, and the 2 cycle that transposes the second and the third element. Again, reading these from right to left, what we're going to get is, first, if I swap 2, 3, ABCD becomes ACBD. Then, swapping 1 and 2 of the result, I'm going to end up with CABD. So I'm just going to write that down. That's the net effect of first applying the 2 cycle 2, 3, and then applying the 2 cycle 1, 2. Now contrast that with what you get by reversing the order in which we apply those cycles. So if I do 1, 2 first, then I'm going to swap the A and the B in my original word. And then doing 2 and 3 swaps A and C in the new word, and I get BCAD. So the net result, again, is different than what it was that I started with. So symmetric group, also an example of group that's not commutative. So where do we stand at the end of this lengthy introduction to what is a group and what are the examples of groups that we care about? Well, so far what we know is what a group is. It's a set of elements, and it's some operation, some rule that turns any two elements into a third element that also is associative, it has inverses, and it has an identity. We saw some examples in which that operation was commutative. We call those groups abelian groups. And some operations in which it wasn't commutative, we would call those non-abelian groups. So the next thing we might start to think about is, okay, if I have an understanding of a group, how do I know how many elements that group has? So something to think about for next time. How many elements are there in, say, the multiplicative group of units modulo n? What about the dihedral group on an n-gon? What about the symmetric group on n symbols? How can we come up with expressions that tell us how many elements are in each one of these groups?